question says program runs in 100 seconds on a machine with multiply operations responsible for 80 seconds of this time. In a design modification, only the algorithm responsible for implementation of multiplication was changed. For 2 bits encoding, 1 was used. In example 1, to 3 bits encoding, both example perform. Yes, also overall speed up. So the whole thing is you just have to find the speed up for multiplication. Now, how did they speed multiplication? They just changed from using 2 bits boot encoding, right, to 3 bit boot encoding. So what is the speed up? Now they give you this example so that you can see the actual difference between 2-bit boot encoding and 3-bit boot encoding, right? You realize that the number of cycles needed, right? I think apart from the initial cycles, which both of them have, the number of cycles needed is 1, 2, 3, and 4 for the 2-bit boot encoding. Whereas the number of cycles needed is what? 1, 2 for the 2-bit boot encoding. So we could confidently say that the 2-bit boot encoding is 2 times, the 3-bit boot encoding is 2 times faster than the what 4-bit boot encoding, because I mean one takes a cycle of 4, the other takes a cycle of 2, right? So the speed up factor S is equal to what, 2. Now once you find the speed up factor, the rest is just your Amdahl's law. The whole thing takes 100 seconds, right? But we are speeding something which takes 80 seconds. So it means that the ones you are speeding, which the ones you are not speeding, are supposed to take a total. The ones you are not speeding are supposed to take a total of 100 minus 80 minus 100 minus 80 seconds, right? Those ones are not sped up. But the ones which are being sped up is the 80 seconds. That was the multiplication, right? But we have to divide by the factor of speed up, right? So this will give you what, I think 20 plus 40, which is 60, right? So it means that the new running time for this program will be 60 seconds instead of 100 seconds. But the question asks you to find the overall percentage speed up for the program. And so the overall percentage speed up will just be the ratio of the original, which is 100 over 60. That will give you the speed up. And when you point this into the calculator, I think you get a value like 1.667, right? Now in percentage, that is what 67.67%, right? And yeah, that's it for question one. Nothing new. Then the next one is, and for these ones, I think they've already been solved, so it's okay. This one has also been solved in previous videos, so that would be that. Then we come to this one. So it says given address 4n in register $0, value h in register $1. Write exactly 3 lines of MIPS code to implement the high level statement a into bracket 0 is equal to h plus a into bracket 2. You may use 2 additional registers, $S2 and $T0. So it's quite basic, right? You want to write this MIPS code, right? So now first thing first, make sure that everything is in register. You see, some of them are in memory. This is in memory. This is also in memory. So to compute this first, make sure that this is in register. Right, so let's fetch this in register. So to fetch this in register, remember that the base address 4n is in $S0, right? So we can first say load word, right? And load word, how you can speak, we need another register to put it. So with the base address in memory, realize that the base address is stored in $S0, right? So So that means that we have to access it, right? And now accessing it means that we have to put it in a variable, right? Now the only extra variables we are allowed to use is what? Either S2 or T0, according to the question. So it means that we'll use those variables, right? So in using those variables, we can say load word, load into what? Let's put it in, let's put it in T0. So load word into T0. Then you see that we are loading this one, right? But it is at location 2, right? Now, in MIPS, this is, how do you call it? More or less like the second word, right? So to make it word align, multiply by 4, so you get 8. So 8, the offset, $0, right? So giving an address in the register $0. So it means that the base address is in that register. Now, the next part you are to do is that you have to also execute this h plus that value. So you've been able to fetch this one into a register. So you are now to execute h plus that value. So to execute h plus that value, the same procedure. You realize that you just say add, right? And where will you store the value? Well, you can continue to add it into E0, right? So that you just overwrite it, or just add into S2 so that we exhaust all the registers. I mean, so that we are using all the registers. So add into S2 the value stored in S1, because they said H1 is in S1, and the value stored in what? T0, the one we just fetched, right? So that will be your second line. Now you have your results stored in S2. So the last part is the A square bracket 0, because you realize that we've moved these two into registers and we've added them. We now have to move them back to memory. So to move it back to memory, use the store word. Right, so we just say store word. And what word are we storing? We are storing word S2 because that's what contains the sum. Right, so we'll say word S2. Now, you see, we are storing at location 0. Right, so 4 times 0 is 0. So $0 S0, because the base address is still in register S0. Yes, and I think with these lines, you have been able to come up with the solution for that. Um, yeah, with those lines, you've been able to come up with the solution for that. Don't think anything will be the problem else. Then the next one is you have to convert this number to decimal, from decimal to hexadecimal, and show how it is stored, right? So this one, I think your calculator can do it. Let me quickly bring up my calculator. So when you put it in X, I think you get C1D. But you see, we are dealing with MIPS, so let's try putting this into 32-bit, right? Let's put this in 32 bits. So this is 4 bits, 8, this is 12, so a total of 12 bits. That's what we have. So it is C1D, right? That's 12 bits. So let's put this in 32 bits, which means we need some more zeros. So 12, 16, 20, 24, 28, 32, right? So yes, that's 32 bits. So 08 and that value, right? So this is now in 32 bits, and you are asked to see how this will be stored in little Indian fashion and big Indian fashion, and you are supposed to use this same. You are supposed to use this memory block, right? So I think you can draw the diagram twice, right? Now I realize that the starting address is 4n and the ending address is 4n plus 3. That's typical of the MIPS architecture. So in storing using a big Indian fashion, okay, let's use the little Indian fashion first. In using the little Indian fashion, right, the lower bits, right, will be stored first before the higher bits, right? So what little Indian will make you realize is that here at this location, right, see, each location can store a total of 8 bits, right, a byte. So this location will store the 1D, because 1D is 8 bits, right? Each two elements in hex is 8 bits. And the next one will store 0C, right? And the next one will store 00. And the last one also store 00. So this will be how it will look like in little endian. However, in big endian, it will change. In big endian, you store the bigger bit first before the smaller bits, right? So in big endian, the first one will be 00. The next one will be 00. Then at this location, you come and store, I think 0C. And then the last location you store what? The 1D, right? So that's the difference between the big endian and the small endian. The storage process is just changed up, right? But nothing new. Then this question, it asks you to you see the opcode and the function for the MIPS instruction SRL. These zeros and zeros, 10 respectively. Give the machine code for the line of assembly code. So yes, they're giving you some information about the assembly code, and you are asked to type the machine code, and it's quite typical. So if you remember quite a bit, the instruction format for now this is an R type instruction, right? I mean they didn't mention it here, but shift right logical is R type. Or even if you can't remember, remember that the opcode is all zero, so it's an R type instruction. So since it's an R type instruction, this is how the format look like. You have the first 6 bits for opcode, the next 5 bits for source one, source two, the, um, the next 5 bits for source one, the following 5 bits for source two, the following 5 bits for what? The destination, the next 5 bits for the shift amount, and the next 6 bits for the function, right? So yes, I know I should rather write it inside, but hope you've seen this diagram. Yeah, so if you can carefully remember this diagram from how type instructions, opcode, RS, yes, so that's the diagram I'm drawing there. So the rest is just to show the diagram, and it's not difficult. So the first part is the opcode. The opcode is just 60, so you can just put the 60 there. 2, 3, 4, 5, 6. Then the next part is the register source one. Now be careful, don't get confused. Here, according to the diagram, there means that the register source one before the register source two, right? Before the destination. But in the instruction, they specify the destination first before the source one and source two, right? So, but there is a bit of trick about um shifts in MIPS, right? We will just specify 0 for the source one, right? The source one register will be just all zeros, right? So think yes, just 5 zeros, and I'll explain later. And the source two register will be the register value for S1. Now, if you remember the table, realize the register value for S1 is for 17, right? And I'm talking of this table. This table, right? You might have seen it a couple of times. So yes, that's what they are used for. So you realize that from S0 to S7, they represent register with numbers 16 to 23. So if S0 is 16, S7 is what? 17. So that's what you put there. So you put the decimal value for 17, right? So that's like um, 1, 3 zeros and 1. Yeah, I think that's 17. Is it already 5 bits? Yes, 5 bits, right? So that's your first one. Now your destination will be T0, right? Now T0 is register number 8, right? And register number 8 is the same as 1, 0. Yeah, I think this is 8, right? Then your shift amount is 8, right? So you put the 8 there. So 8 is um right, so that's your shift amount. And the last part is your function. The function they give it to you in the question, which was what? I think 4 zeros, 1 0. Right. So yeah, more or less this is what you have for the instruction format. And there are several examples like that, right? You can view here. So realize that this example is the shift logical left instruction, right? Now I realize that these are the two registers. However, this is the destination, this is the source 2. Source 1, they put 0 there, right? They don't specify any register for source 1. you put 0 there. Then you already know that source 1 is register number 17. Then RD is what? Register number 8. You put your shift amount and your funds as well. So that's basically for that question. So if you have to give the machine code, then you just have to write all of these ones as one long thing. And usually you can even convert to hex to make it nicer, but we'll not be doing that. Then the last part is write down the set of values for the control signals when the processor in figure 4 is handling the indicated instructions. Use 0, 1, or X, where X is don't care. So things like this, I think we should take our time, and you have to remember a bit from, okay, you are fortunate, you have the MIPS data part, right? Now, when you remember the MIPS data part, and even if you don't know what it does, right, just go and look at the signals, right? So for example, the first one is regdist. Regdist, regdist is, I think, this signal, which is going back here, right? Now you realize that this signal is trying to select either 15 to 11 or 20 to 16, right? And you realize that in in our format instructions, our destination address is what? 15 to 11. In I type instruction, the destination address was usually the 20 to 16, right? So here reg this has to be 1 for this to work. So here it has to be 1. Then the next part is jump. And you can even look at the jump. Well, this is a this is a multiplexer select signal. Now we can't assume it to be a don't scare, right? And this instruction is not even a jump, it's an add instruction. So here will be 0. Now the one thing is that for something like jump, you can fill the rest of the table for it, right? Because you realize that it would always be 0 unless it's a jump instruction, right? So you can just quickly fill the table for it, and you are okay with that. Then the next part is branch, right? Um, the branch will also only be 1 when the instruction is a branch instruction. So here is 0, here is 0, um, here is 0. Sorry, here is 1, right? Whether or not the branch is taken, it is 1. It is the output from the ALU, which will show whether it is 0 or which will show whether it is actually taken or not, right? So here has to be 1 and here has to be 0. So it means that these two are always 1, because when you check the branch signal is controlling this, right? Now there is a comparator in the ALU, so it will compare. If the two values actually compare, then it will set here as what 1. Like it will, if both of them subtract and give 0, it will send 1 to here, right? And if it is a branch instruction, then the instruction would accept here as 1 and to take the signal part, right? Now, whether or not the branch is taken or not, I mean, it is still a branch instruction, right? So it means that the branch has to be accepted. Then the next part is memory. And R does not even read memory, right? Yeah, R does not read memory. So go and check the memory signal. Um, memory signal is that, and I think, yeah, I think it's this one. And the memory signal, it's not a multiplexer select, it's a control signal. We can't just allow anything for it. So let's specifically make it 0, right? The next one is mem to reg, right? So the mem to reg is this signal. You realize that it's a multiplexer select signal, right? And the depending on the value which is accepted from it, we would either be taking our output from the ALU or taking our output from the data memory, right? Now, since we want to be taking our output from the ALU, right, we have to set the mem to reg towards 0, right? Because the add will just have to fill mem to reg is 0. Then the next one is the ALU up. Well, for our type instructions, the ALU up, the ALU up is mostly assumed to be 1 0, right? Yes, so you can just put 1 0 there, and it's a 2-bit something. It's a 2-bit signal. And the next one is memwrite, and this one doesn't write to memory, right? So you have to be careful of memory. So put 0 there, don't put donkey. Then the next one is ALU source. Now you realize that this is our format, and our format we read from this one and this one. We don't ALU source is the signal that is controlled by that control this multiplexer. So it means that we have to select 0, right? So ALU source has to be 0 specifically. The next one is reg write. Yeah, our format we write to register. I mean, when we finish our evaluation, we take our result back to the register. So our format we write to the register. So I think you put 1. The next one is PC source. So you're going to look for PC source. Um, PC source. Oh, I can't find PC source in the diagram. Um, well, can't find PC source in the diagram, but usually, even if PC source was drawn along here, let me get a diagram with PC source so I explain better. Okay, so but most diagram actually, PC source actually happens to be the output of this, right? So the output of this is PC source, right? So that's PC source. I think they didn't label that in the diagram, right? So yes, that's the output. And I mean, this is an R format instruction add. So just put 0 for the PC source. Don't put don't care. Because I mean, when it is one, you'll be in danger, right? You'll be selecting something there. And the next instructions we do is the load word. Well, for load word, it's not really different, but you realize that um we've already done I think 2 of them, right? So load word, reg dist, and we have to put 0 there, right? Because remember load reg dist was selecting between either the 20 to 16 or 15 to 11, right? Yes, and for load word, we use the 20 to 16 part for the destination. So yes, here has to be 0. Then the next one is memory. Does load word read from memory? Yes, it does. So 1. Then the next one is mem to reg. Does load word take data from memory to the register file? So go and look at the mem to reg. It is, I think it is this signal, right? And yes, it takes from memory to the register file. So we'll be taking from memory. So we'll choose 1, right? So that's the one you see in 1. Then the next one is ALU up. So what's the ALU up for load word? Well, um, the ALU up have been categorized. The ones which start with 1 are all for alphabet usually. So load word will usually start with 0. So usually they put 0 0 here. And memwrite, does load word write to memory? Of course it does, right? It writes to memory. So let me see the memwrite signal. Sorry, load word doesn't write to data memory. It writes to register for not data memory. So memwrite has to be 0. Very sorry about that. Then the next one is ALU source. Well, load word is the type of instructions we take from the same extended and not R2, right? So ALU source has to be 1. So I think you have to put 1 there. And the next one is reg write. Reg write, and that's what the write register for. Yeah, of course, it writes. And the next one is PC source. I mean, you can't put don't care here. Whoever did this paper is really dead. You can't put don't care here because you have to make sure that you are choosing PC plus 4, not any branch instruction. So you put 0 there. Then the next one, I think let's continue filling it, right? So the next one, let's continue filling for the PC source so that we don't come thinking. So the PC source for branch, when it is taken, then the PC source will be 1, right? Because when it is taken, it means that when it's compared, this 0 was activated and this branch was also activated. So the PC source will be 1. Now, when the branch is not taken, then the PC source will end up being zero, right? So that is also differentiates not taken from taken. Then the last part is jump. Well, for jump, let's see the PC source. For jump, if the instruction is a jump instruction, it doesn't matter what you put for the PC source here, right? We would end up choosing the uh, jump target address, right? So you realize that this multiplexer will be useless in the case of jump, so we can put a don't care here, right? So then yeah, so we filled for the PC source so that we can't be worrying about that. Now, um, read write. These instructions don't write to memory, so we can put zeros, right? They don't write to register file, so we can put zeros. Now, ALU source. For branch equal instruction, let's go and see the ALU source. Well, for branch equal instruction, the ALU source will be from what needs to like the element to give it. It will take it from these two registers, right? So the ALU source will be zero here, right? So yes, so the ALU source will be zero, right? And it's also be zero here because it means the same branch equal instruction. The ALU source for jump. Well, jump doesn't even use the ALU, so it doesn't matter what you put there. So let's put a don't care here. Right? Yes, jump doesn't use the ALU. You can just see. You come here, we compute the jump target address. It's not actually a computation, it's just concatenation, right? We just shift left and here, so we don't use it. So you can put a don't care. Then the next one is I think ALU up. Yes. So the ALU up for the ALU up for the ALU up for branch equal instructions are usually just 0 1. Yes, because they will subtract the distances 0 1. Now the ALU up for jump doesn't really exist because I mean this guy doesn't even use the OU, so we can put don't care there. Then mem to reg, and this one doesn't use the register file, right? So it's don't care. Then this one also doesn't use it, so don't care. This one doesn't use it as well, so don't care. Right? Now mem read, and when it's a read or write signal, I mean we can't be careless, so let's purposely put zero, but I'll confirm. Then the last part is the reg test. I mean this guy don't care where you write because they don't even write to memory, so this is just a don't care, and this is also a don't care. Yes. So at the end of the day, I think this should be the control table. Should be similar to something like this. Should be similar to something like this. I haven't gone through the whole thing yet, but at least you should have something similar to this, where you see your don't cares and everything. Yes, so that's all. And these ones are in the pipeline. I think those are not part of the questions he said will come. Then this one is the last one. So this one is under memory. The last part says consider a cache 15 kilobytes with block size 256 bytes. 256 bytes. The size of main memory is 128 kilobytes. So it says find the size in bits of each field in main memory address for each of the following mapping techniques. So you are using direct mapping for the first one. Let's find some parameters. So now let's find how addressable is memory. So number of bits which we use in number of bits for main memory is equal to 128 kilobytes is what? The same as 2 raised to the power 17, right? 2 raised to the power 17, right? So in essence, um, we will be using 17 bits to come and look in the cache, right? So in essence, we use 17 bits, right? Would have been using 2 bits, right? But the question is a bit twisted, so that we use 17 bits. Now the next part is um the case for direct mapping, right? So Now, for direct mapping, you have to find the bits for tag as well as index, right? So let's find index bits. Index bits. Now you have 16 kilobytes, and the size you are dividing into what blocks of what 256 bytes. So in essence, you get 16 kilobytes the same as 2 raised to the power 2 to the power 14, right? And 256 bytes is the same as 2 to the power 8, right? So in essence, you get 2 to the power 6, right? Now, which means you need a total of what? 6, 6 index bits. You need a total of 6 index bits. Yeah, so we'll have a total of 6 bits for the index bit. That is for the direct mapping. Now, when we consider the tag bits for the direct mapping, we have to do 17 minus the number of index bits, which is 6, right? Plus the byte offset. Here we have 256 bytes, right? So we need a total of 8 bits to offset it, right? Yes. So we get a byte offset of 6 plus 8. So we get, I think 6 plus 8 is 14. So 14 minus 17 is, 17 minus 14 is 3, right? So it means that now our tag bit is equal to this, right? And our byte offset is the 6 we calculated. So byte offset is equal to 6, right? And I know the byte offset might sound confusing, but the byte offset, you see, if we are using MIPS, right? All the time you were using one word, so the byte offset was because one word is what 4 bytes, right? So 2 is the power 2, so that 2 there is the byte offset. Now this one you are using some, I don't know, weird architecture, and I think each word is 256 bytes, right? So 2 is the power 8, so that 8 there will be your byte offset. I think something like that to make sense. So yeah, so this is for the direct map. Now for fully associative, uh, so I think let me do it here. For fully associative, nothing much changes, right? But fully associative, one thing you should know is that we don't use any index bits. Why? We are trying to search through the whole space anyway, so why use an index bit? So for fully associative, index bit is 0, right? Now, this will also make our byte offset will still be 6. So byte offset will still be 8, sorry. Wait, did I say our byte offset was 6? It's supposed to be 8. 2 raised to the power 8 is 256. Right, yes. So our byte offset will still be 8. And then um our tag will just be 17 minus 8, right? Because our index bit is there. So 17 minus 8 is 9. So we need a 9-bit tag. So 9-bit tag, right? So that's for fully associative. Now let's consider two-way associative. So for two-way associative, the procedure doesn't change much. So for the last one, it says two-way fully associative. Two-way set associative. So for two-way set associative, you know, um, the shortest way the shortest way you can get your answer is that for when you increase the associativity um, from by 2a, right, the number of index bits will decrease by 1, and the number of tag bits will increase by 1. Now when you go ahead to 4-way, it will decrease by 2 for the index bits, increase by 2 for the tag bits, right? So that's fine for the associativity. So this one, two-way associative. So our original index bit, which was what 6, will now become 5, right? And our original tag bit, which was what 3, will become 4 tag bits, right? And our byte offset and is our byte offset to be 8, right? So I think with that we have it. So in fully associative, I mean your index bit is 0. Your byte offset is